Hello, welcome back. Okay, quick enrichment lecture. Today I'm gonna do some little thing on the cross twins. I received a couple of emails, guys, from some of you that had done a lecture. I think it was on the integral, if my memory serves me well, of 1 over 1 plus x to the 6 plus 1, and I did mention this this item, and a few of you got a bit confused. And first of all, I want to just revisit not this particular integral but a different integral and explain this a little bit more thoroughly. However, if you have any questions on what I'm doing, the best way is not to send an email, because sometimes I'm very bad. It takes me ages to reply, so it's best to actually put a comment at the bottom of the video, and perhaps somebody else who might have understood what I was going on about might take the time to actually answer you. Okay, what we're going to do today is we're going to look at a very tough integral. Indefinite integral is the indefinite integral of the square root of 1 plus the tan of x, or square rooted, which will illustrate this particular kind of method. Is the ugliest of this lot, so I hope you stay with me on this particular one. So first of all, let me explain what is the cross twins. I'm gonna write something here first of all. Okay, and it's basically a scenario that arises a lot of the time in integration, particularly when we're having things like x squared or 1 over x squared, usually on the denominator. We can actually set up two integrals. This is what the cross twins are, which look something like this. Okay, I'm going to write them as separate integrals, just to get the idea. And this is what they ought to look like. This is the ideal scenario. We're going to have some completed the square form at the bottom. So we're going to have something which looks like x, let's say x minus, let's put a k there, because in general it usually would be a 1, but k is the most general case. K over x all squared, plus another constant, which we actually, I'm going to write as a capital A. It doesn't have to be squared necessarily, although we will sort that out in a second. And on the top, it has to be something very special. It has to be 1 plus k over x squared. Minus here, plus there. And the other way around on the other integral. So on the other integral, we ought to have an x plus k over x all squared, plus a different constant there. This could be positive or negative, by the way. Yeah, it doesn't have to be, and it doesn't necessarily mean it's a positive thing. But on the top now, we're going to have the negative of that, so it's 1 minus k over x squared. There's some kind of symmetry in all of this. And what's the whole point of all of this? I mean, this is the question. If you look carefully on those two integrals, if you look at what the interior of this bracket differentiates to, it will differentiate to 1 plus k over x squared, and the other one exactly the same. So this is kind of like, we lead some kind of substitution, as you will see in the example I'm going to present tonight. And this will happen on the integral of, I think I've done the other day, this particular one, with this particular method. It wasn't too bad, actually. The 1 over x to the 6 plus 1 is okay. This one is fairly ugly, so we have to keep track of things very late in the day, so I hope I don't do mistakes on this. So let's get on with it. So the first thing, with something like this, I'm going to start with the substitution. My intention is to just get rid of this square root. This is very ugly. So I'm going to do my substitution here. T is equal to the square root of 1 plus the tan of x, or square rooted. I'm going to square it before I differentiate. So t squared is equal to 1 plus the tan of x. I'm probably going to move the 1 to the left. It's just looks a bit better before differentiation. Now we're going to differentiate it. So we're going to have 2t dt is equal to sec squared x dx. And I'm going to get something sensible. I just want to get rid of this sec. So I'm going to write it as 2t dt. Sec is, of course, a 1 plus tan squared x, identity, dx. But then if you look at what tan x is up here, actually, I can write this as 2t dt is equal to 1 plus the tan is all of this t squared minus 1 all squared dx, and probably I will simplify before I put it across. So 2t dt is equal to t to the 4 minus 2t squared plus 1 is a plus 2 bracket dx. So lastly, we're going to have our dx, which we got in there, simplifiable to a 2t over this quartic, which is t to the 4 minus 2t squared plus 2 dt. So this substitution was nothing to do with the cross twins. All we're doing is we're trying to first of all clear this a little bit, because it's a mess. The square root there is just a mess. Okay, so let's put things in. So all of this, we called it t, and our dx is all of that. So it's basically t times that. So I'm going to write straight away as 2t squared, the whole thing over t to the 4 minus 2t squared plus 2. Let me just check the signs. Minus 2t squared plus 2 dt. So this is now, I'm going to just clear this board a little bit. I'm going to just leave the substitution for when we're going back at the end of the integral. These things, we don't need them. There's no limits to change. So have a look at this integral now. And you know, I mentioned at the beginning what the cross twins is all about. It's about expressions that have lots of t squares like we got in there. You might say, what about that t to the 4? It will become a t squared. We need it as a t squared. And this is what we're going to do next. An obvious step, which is just to divide top and bottom of the integrand by t squared. So we're going to have a 2 over, and then we have t squared minus 2 plus 2 over t squared dt. Okay, what do we do next? Remember, we have to do two integrals, and conveniently this actually is although it's very, very ugly, this too is actually quite convenient, because what we can do, I want to move this integral up here now. Okay, so I can actually write two separate integrals, exactly the same denominator, of course. So the 2, I'm going to split it as 1 and 1, and the denominator, of course, exactly the same. It's going to be t squared minus 2 plus 2 over t squared, and exactly the same on the other one. And now I'm going to create that ideal scenario of this particular setup. So I'm going to come off the integral now. I'm going to just do some workings here. And I'm looking at this particular expression. And I'm looking at the t squared plus 2 over t squared. And I'm going to write here t minus, I want this to be something squared. So I have to write, unfortunately, this is very ugly, a square root of 2 over t, all in a bracket, squared. So let's see what that gives me. That will give me, of course, a t squared minus, the t's will cancel, 2 lots of the square root of 2, plus, of course, my 2 over t squared. Okay, let's look at what I've got up there. I need to create this somehow. So I'm going to do it in steps, because I don't want to make a mistake. I'm going to subtract, first of all, this to the left. So first of all, actually it's not subtract, call it add, 2 root 2. That's gone left. And I'm leaving myself there with just t squared plus 2 over t squared. And then I'm looking at this denominator, I need a minus 2. So my last line, I'm going to subtract t minus root 2 over t plus 2 root 2 minus a 2 from both sides. So this is now my denominator here, and I've got this mess that I'm saying in there. Okay, I forgot the square there. So what I'm going to do, underneath this particular integral, I'm going to write some of this. So I'm going to write it as t minus the square root of t, because I'm going to wrap some of this off so we don't lose it, all squared. And I'm going to write there, bear in mind this quantity is positive, 2 root 2 minus 2 is definitely positive, so I'm going to call this a squared, and I'm going to write it up there because this is just a mess to be carrying around throughout the integral. So I'm going to call a squared from now on starts as so it stands for 2 root 2 minus 2. So up here in green, and remember this is positive plus a squared. So this denominator is the same as that. Okay. What about this denominator? Well, it's exactly the same, but I'm not going to write it like this. For this particular one, and I don't want to rewrite the workings again, I want the cross, basically, the opposite kind of thing. I want it symmetrical, so I want this to have a plus there. So I'm going to start with this expansion. How does that change things? Well, this will be plus here. Okay, so we go to this line. What did that do on this line? I took this to the left. So if I take this to the left now, this 2 root 2 will be, of course, negative. And I'm still the same, t squared plus 2, blah, blah, blah. It's all good. And then I need to subtract 2 from both sides. And don't forget, this has to be now a plus. I forgot to actually change that to a plus. Okay. So what we've got now is exactly the same. Well, not exactly the same. Something very symmetrical. We got 2 root 2 minus 2, which again is sorry, plus 2, I beg your pardon, because we're adding now 2 to both sides, or we're subtracting 2, no, sorry, we got a minus 2, so I'm going to bring this now to the left, so it's going to be, for this particular one, a plus 2, okay, sorry about that. So this particular one, sorry, have I made a mistake in that? Just bear with me, because I've tried to do too many things at once. Let me just run through it again very quickly, so I'm happy in my head. T plus that is definitely that expansion. Okay, plus I'm subtracting 2 root 2. Why am I doing that? Basically, I'm bringing that to the left. That's all good. That leaves me those two terms. And then I need, so of course that is now a minus, so that's always a mistake. And now I need to subtract 2 from both sides. So that's rubbish, or pure rubbish. So recovered. Just run the video back if you want, guys, just to check that this is correct. It's correct now. And bear in mind now, this is a negative quantity. I can write it as minus 2 root 2 plus 2 with a minus at the front. And this quantity now is positive. I'm going to label it as b squared. And I'm going to write what b squared stands for. So b squared now is equal to 2 root 2 plus 2. So very, very similar, but not the same. So this particular denominator, I'm going to write it differently. I'm going to write it in green. So what do I have in there? T squared plus 2 over t squared minus 2 is equal to t plus the square root of 2 over t, all squared. Now I have a minus b squared. Okay, and let's rub off these blue workings, and let's look now at what I've got up there. Now, notice, although in green, these two expressions look well, not completely different, but kind of like analogous, but not the same. They're in fact exactly the same. So I can actually balance these two integrals by adding and subtracting the same quantity. And keep in mind, because I got a minus here, I'm going to put a plus. And remember what I want. I want something which will create a derivative. So the quantity I'm after is root 2 over t squared with a plus, because I got a minus here. But for this one, I'm forced to do it, but also I need it because I need to cancel it. So it's exactly the opposite. So that now will differentiate to that. And it still balances, it's still okay. And my denominator now is in fact, I don't want to be rewriting it again, otherwise the board will not fit everything I need to do. So I'm going to write it actually in black, but still on the same line. I'm just going to move the green workings. So that's t minus root 2 over t, all in the bracket squared plus a squared. And this is, in analogy, t plus root 2 over t, all squared. And now it's a minus b squared. And I've forgotten the dt there. I do apologize. I just saw it just now. Okay. So the scenario of the cross twins has been accomplished, and now of course we need to know why we've done it. Of course I mentioned the differentiation of that to that. We're going to use a substitution for each of them. Okay, so I'm gonna let you equal to t minus root 2 over t. So t minus root 2 over t. We're going to differentiate it. du is 1 plus the square root of 2 over t squared bracket dt. And if you look at this quantity, here it is. So I'm going to go to the next line and fill this integral in so we can keep track of things. So that's still equal to, all of this is my du. I call this u, so that's u squared plus a squared, which you can see we got an arctan now. Plus, for the other integral, I'm going to use a similar substitution. I'm going to call v is equal to t plus the square root of 2 over t, and therefore mad dv by construction is going to be 1 minus the square root of 2 over t squared dt. And if we look at this quantity here, that's our dv. So this integral also transforms. I call this a v squared. It's a minus b squared, and I've got a dv. Okay, so let's have a look at all of this so far. All right, that's a straightforward arctan. This we can go into partial fractions. It's not too bad. It's going to go in eventually into logs, v minus b, v plus b, and it's probably the one I done with the 1 over x to the 6 plus 1 the other day. I did go partial fractions, and I did mention hyperbolic arctangent or hyperbolic inverse hyperbolic cotangent, arccoth. I'm going to go hyperbolic arctangent this time. So the way to do it, I'm going to not waste a line. I need this to be the other way around. So I'm going to pull a minus in front of the integral. There's my minus, and now this will be a b squared minus v squared because I want this particular form. Okay, so integrating now, this is 1 over a, the arctan, normal arctan of u over a, and I will need to trace my substitutions obviously at the end, minus, this is now I'm going to go as an arctange, so that is going to be 1 over b, the arctange of v over b, plus c. So the integration now has been completed. It's just a mess now to try to put all these things back into x. So we'll do that step at a time. I hope we don't make any mistake now. If I make a mistake, please forgive me. It's very, very late at the moment, but the whole point of this lecture was to actually explain a little bit about this particular technique, okay? And I think it's probably just one of the worst integrals that you can do. It's very, very messy, square roots, total mess. Okay, so let's trace our substitutions. First of all, u's and v's, they're up there. So I'm not going to put the a's and the b's just yet. I'm going to do it on the next line. The a's and b's are constants, of course, so I'm going to do that at the end. So this is equal to 1 over a arctan, and u is t minus the square root of 2 over t, the whole thing over a, minus 1 over b, arctange, and the v is t plus the square root of 2 over t, the whole thing over b, plus c, of course. A little bit of an in-between tidy before I put any more things in. I'm going to multiply top and bottom of the argument by t, so it's going to give me a 1 over a arctan t squared minus root 2 over a t minus 1 over b arctange. Some people call it arctan. I call it tange. I don't know what you call it. The correct name, of course, is the inverse hyperbolic arctangent. Not the inverse hyperbolic tangent, not arctangent. The inverse hyperbolic tangent. Okay, so same thing with this one. T squared plus the square root of 2 over bt plus c. Okay, we don't need this line anymore. Nope. Okay, we got everything we need up there. So what do we have now all together? I'm gonna start putting in the constants. It's gonna be a total and utter mess. A 1 over a. Okay, so that is going to be now a 1 over, that's a squared, so it's going to be the square root of 2 or root 2 minus 2. So that's my 1 over a. Arc tan t squared actually kills a square root up there, so I'm gonna have 1. I'm gonna put the 1 from the 1 plus tan x first, so I'm gonna write it as 1, then the minus root 2 plus the tan of x, that's the numerator, and a, oh my god, this oh gosh, is going to be the square root of this thing here again, 2 root 2 minus 2, and the t is the square root of 1 plus tan x. I did warn you, it's not going to be pleasant, but I hope it's correct. I hope I haven't done any silly mistakes. I hope there's no conceptual mistakes if I made mistakes. They're just possibly signs or factors of 2 or something silly like that. So minus 1 over the b is going to be now the square root of the symmetrical one. So square root of 2 root 2 plus 2, all inside the square root. And then I got hyperbolic r tang of t squared is gonna square this out. So I'm gonna have a 1 from squaring the square root. I'm gonna put that first. So I'm gonna have to switch into blue pen because my black pen is dying at the moment. So 1 from there, when I square it, plus root 2, that was already there, plus a tan of x, which came from squaring this quantity here, over bt. What is b? b is the square root of 2 root 2 plus 2, all in the square root, and t is of course the square root of 1 plus the tan of x inside the square root, and let's not forget the c. Quite something. Quite disgusting, I did warn you. I hope it made sense. I mean, the last bit, of course, there's no elegance to it. I mean, if you look now at the one I've done the other day, it's much nicer, much cleaner, okay? So this is the cross-twin methods. And on that note, guys, who's laughing now? We're certainly laughing because we actually managed it, hopefully without any problems, okay? I'll see you very soon. I hope you find it useful, okay? Bye for now.